Alright guys, today we're going to talk about derivatives, and derivatives can also be called the slope-finding equations. We'll also talk about second derivatives, which we can call the concavity-finding equations. So let's say I had an equation such as y equals 3x squared. Okay? So y equals 3x squared, I could call this the height-finding equation, right? Because y tells me a height for any given value of x, right? So if I plug in a value of x such as 1, then this equation gives me a height of 3. Or if I plug in a value of x such as 2, then this equation gives me a height of 12. So based on this height finding equation, y equals 3x squared, we could take its derivative, which would give us a slope finding equation, which would give us the slope at any point on that curve. And we could do a second derivative, which would tell us the concavity of that graph at any point along the curve. So if we have a graph like this one, obviously finding the slope is pretty easy because it's a straight line. Let's just make up something. Let's say that this was a graph of y equals 3x minus 10. I don't know how realistic that is for that graph, but it could be something like that. Okay, then obviously we can find the slope anywhere on that line, and the slope anywhere on that line is always going to be the same thing. And so for this particular equation, if we did the y2 minus y1 over x2 minus x1 for any 2 points q and p on that line, we would always find that the slope would equal 3. And so we can actually say that the derivative of this equation, the derivative of y with respect to x, would simply equal 3. And so the derivative of any linear equation is just going to be the slope of that line. We'll talk about y in just a minute. So now we have something a little more complicated. So now we're looking at, we have graphed some function represented by this curved line right here that I'm tracing in pink. Okay? And so let's say we want to know the slope of that line at this point here, P. Okay? Then what we'll notice is that first right here we've shown this average rate of change between P and Q. So we have this point P and this point Q, and we've drawn a straight line between them. Okay? And then the other thing we've shown here is we have the instantaneous rate of change at point P, and that would be the slope of the tangent line to point P. And so we notice that that slope of the line P to Q, the line straight from P to Q, and the slope of the tangent line, of course, are not the same. But what we want to do is figure out a way to find the slope of that tangent line. So once again, I want you to notice that we have our point P and our point Q along our curved graph, and we have two lines shown there. One is the tangent line to point P, which is really our goal to try to calculate that, and then the other line is a line straight through P and Q. And I want you to notice on the next slide what happens when we move Q down closer to P. So now we've moved Q to the left in there closer to P, and what you'll notice is that these two lines are much more similar in slope. So as that second point Q gets closer to P, the line PQ gets much closer to the slope of the tangent line at P. Alright, so here we've labeled points P and Q, and we've given them values for their x and y values. So P is at x value x, and y value, which would also be called f of x, right? It's a function of x. And then Q we've called x plus some extra value h, and then so that's going to be the function of x plus h. And so slope then is going to equal y2, and our y2 is going to be f of x plus h minus y1, which is just going to be f of x, divided by x2, which is going to be x plus h minus x1, which is just going to be x. So what we're trying to do is find that slope value when P and Q are getting really close together. So what we're actually trying to do here is we're trying to take the limit of that equation as that value of plus h approaches 0. So what the derivative really is then is the limit as that value h approaches 0 of f of x plus h minus f of x divided by, the two x's on bottom cancel out, so divided by h. And that's really then what a derivative is. Derivatives can be kind of shown two ways. One way to do it is we can call that f prime of x. So we'd say f prime of x, the first derivative of x, so the limit as h approaches 0. Or the other way to do it, and the way we'll do it in this class, is we say that that would be called dy over dx, the derivative of y with respect to x. So now we're going to try this process with a real equation. This is the equation y equals 3x squared. And as we can see there, the slope of the line is constantly changing. It doesn't have a constant slope. And so what we're going to do is we're going to find the derivative of y with respect to x, which will give us the slope anywhere along that curve just by plugging in a value of x. Alright, so we have our height finding equation, y equals 3x squared. And then our slope finding equation, then, dy over dx, should equal the limit as h approaches 0 of 3x plus h squared minus 3x squared divided by h. So what I'm going to do next is just do the algebra so I can simplify some things. So now that we've distributed everything out, we can see that this 3x squared and this 3x squared cancel each other out. And then we can see that all the terms left have h's. And so this h, that squared, and that h cancels. So now what we're left with is that our derivative, dy over dx, equals the limit as h approaches 0 of 6x plus 3h. And of course, as that h approaches 0, that value just becomes 6x. So the derivative of 3x squared then is 6x. Okay, so here's the derivative we found for 3x squared, and what you're going to end up noticing is that if y equals some value ax to the n, then dy over dx, the derivative of y with respect to x, ends up being n ax to the n minus 1. And you can see that if you look back up here. If we take our 2 and multiply that, it's going to be 2 times 3, right? So that's our NA times x, and then to the n minus 1. 2 minus 1. So that's going to be 6x to the first, which of course we just write 6x. Alright, we also spoke earlier about the second derivative. So if y equals 3x squared, then the derivative of y with respect to x ends up equaling 6x. Okay? So the second derivative of y is just going to be the derivative of dy over dx, and we write that d squared y over dx squared. And so if we're taking the second derivative of y, what we're really doing is taking the derivative of the derivative. So we can think of this 6x right there as being 6x to the first power. And so we're going to do 1 times 6 times x to the 1 minus 1. And so of course that would then be 6x to the 0. But anything to the 0 power is just 1, and so that value is 6. And so remember that this is a concavity finding equation, and what you'll notice there is that we get a positive value. So that would show that the curvature of 3x squared is always concave up. If that value comes out negative, then that would mean that it's concave down. Alright, so that's the very, very basics for derivatives. And we'll be looking at these when we're talking about the relationship between position, velocity, and acceleration next week. See you then.